why don't we do an audio activity? Tim, can you speak some so we can know?
Can you hear me, Richard?
Yes, I can. Okay, I just wanted to make sure. Okay.
I'm having a difficult time hearing you, actually.
Really?
So if you speak a little louder, I think it'll come through. Right now,
Okay.
It's pretty dim.
Let's see, maybe it's
On the wrong one. That better?
There we go.
Yeah, just had the wrong setting for the wrong microphone. Okay. So today's agronomy seminar is a little bit more unusual than many of our seminars have been. Today's speaker is Tim Griffis from University of Minnesota, Twin Cities. He's received his PhD from McMaster's University in Canada, and he's currently a professor of biometeorology in the Soil, Water, and Climate Department at the university. His research interests include development of micrometeorological and optical stable isotope techniques to trace the flow of carbon, nitrogen, and water between the land and the atmosphere, to study the reactive nitrogen cycling and the biosphere-atmosphere interface, to study the budgets of methane and carbon dioxide, especially in tropical forests and peatlands, and he's also doing biophysical modeling of trace gas exchange in the land-atmosphere system. So today we welcome Tim, and I'll turn it over to you, Tim.
Okay, thank you, Richard. Good afternoon, everyone. It's a pleasure to visit your department, even if it's virtual. It's a great opportunity to share some of our ongoing work, and today we're going to be talking about how we constrain regional nitrous oxide and ammonia emissions using some relatively long-term tall tower observations and with the help of some chemical transport modeling. Oops. I'd like to acknowledge first my collaborators and especially my postdoctoral and graduate students who've really helped shape this recent work. Especially, I should mention Cheng Hu, Zichang Chen, and Peter Turner, who've made really significant contributions to this work. And I also want to acknowledge funding from various agencies who have helped us maintain these relatively novel observations. So the nitrogen story I want to tell today largely involves tall tower measurements that we've been making. This goes back to about 2007. So with the help of a National Science Foundation Career Award, I was able to work with Minnesota Public Radio and put instruments on this 244-meter tower. And so the Minnesota Public Radio has been a very good collaborator and very supportive of our work. We rent space off the tower, which is not cheap, but it has really helped us sort of advance, I think, our understanding of trace gas emissions in the upper Midwest here. Back in 2007, we started making carbon dioxide and isotope measurements of carbon dioxide from the tower. And then in 2010, we did some updates to some of the lasers that we had so that we could measure nitrous oxide. And then in 2017, we added more capacity so that we could start measuring ammonia from the tower. If you look across this landscape, there is some remnant forest, but generally a significant fraction of this, what we call the source footprint of the tower, is dominated by agricultural systems. So here we're looking south, and as you look south, you can see the transition into mainly agricultural lands. If you look down to the lower left panel, you can see the little X here, which marks the spot, the location of the tall tower. And then what I've plotted is what we call a concentration footprint. And now this is a monthly average concentration footprint. So if you imagine us tracing particles backward in time, over a period of a month from this tall tower. So if we release particles and we follow those back in time, you can see that the influence of the surface is really a continental influence on these observations, but really it's this sort of dark, hotter reddish area here that these tall tower observations are most sensitive to. And so we use these observations really to interpret what is happening here in the upper Midwest. If we look at the base of the tower, we have instrumentation located right inside the Minnesota Public Radio tower facility where they communicate on the air. And so it's a really nice environment to work in because it's kept at a very stable temperature. So we've been using tunable diode lasers that you see here. This one down here has been measuring methane concentrations in the atmosphere. This one here is measuring nitrous oxide and carbon dioxide. And then we have other lasers, which I'll show later, that we use for the ammonia measurements. Air is being pulled down this tower at very high flow rates and at relatively low atmospheric pressure. And then it gets subsampled here at the base of the tower into these various lasers. We're measuring at about 10 times per second. So we're quantifying what's happening in the atmosphere, pretty high frequency. And then we take those observations and average them down to hourly averages. So right now, we've been making measurements of nitrous oxide since about 2010, and have over 100,000 observations that we've made to help us characterize what the regional budget of nitrous oxide is. If we look at this figure, this is where I have averaged all of those very fast nitrous oxide measurements from the tall tower and plotted them as a function of time. And so each of the gray circles represents a weekly average value. I'm also showing sort of the lower, the 10th percentile and the 90th percentile, and then the annual average values you can see here in black triangles. And so you can see that there is some year-to-year variability, but this trend here, that the trend line shows that nitrous oxide has been increasing at about 0.8 parts per billion per year. And this is an excellent agreement with global observations and a recent analysis by Tien and others that was published in 2020 in Nature. They document that the global increase in nitrous oxide is somewhere between 0.68, 0.98 parts per billion per year, or roughly a 2% increase in nitrous oxide concentrations per decade. Okay, so we are concerned about this because nitrous oxide exerts the third highest radiative forcing of the long-lived greenhouse gases. And also, it's the major sink, or the major sink for nitrous oxide is stratospheric ozone depletion. So it's the double whammy gas. It's increasing, helping to increase surface temperatures, and at the same time, thinning the stratospheric ozone layer through chemical reactions. Because of N2O's long atmospheric lifetime, about 120 years, this means that today's management decisions and farm policies really have far-reaching consequences for the Earth atmosphere system. And so these observations are really important for us to help establish a benchmark so that we can assess whether or not mitigation scenarios are working. The other thing I'll comment later in today's talk is the increasing concentrations that we also see related to ammonia. And of course, ammonia is implicated in aerosol formation and has been linked to acute human health problems, costing the United States about $36 billion annually. So this is a grand challenge. We have an increasing population, increasing demands for food, fiber, and fuel. And all of this is then complicated by climate change. We're facing, especially here in the upper Midwest, we're getting warmer conditions and much wetter springs, which really has implications on how much nitrogen leaves these systems or leaks from these systems, and how we keep track of those emissions then to the atmosphere. We know that a lot of the trend that we see in nitrous oxide emissions is being driven by the global use or demand for synthetic nitrogen. So here I've plotted up the forecasted demand, which I've been keeping track of for several years, and also the FAO stat product that looks at estimating the actual global use of synthetic nitrogen. And if you look at these trends, I plotted the trend line here from 1995 to 2019. It indicates about a 1.4 teragram per year increase in the amount of nitrogen being used. And so that by about 2030, we're on pace to reach about 120 teragrams of synthetic nitrogen use being added to the global system each year. So that's a significant amount. And we know from previous work, Smith and Paul Crutzen and others, that roughly about 4% of this anthropogenic nitrogen ends up in the atmosphere as nitrous oxide. So in terms of a sort of global top-down constraint on N20 emissions, they get the best match by looking at about a 4% emission factor applied to anthropogenic nitrogen, suggesting that agricultural global emissions of nitrous oxide nitrogen is about 4.1 teragrams. If we go back to Tien's work that was just published in 2020, this is probably the most comprehensive top-down global inverse analysis of nitrous oxide that we have to date. And what they show in this paper is that bottom-up estimates, for example, calculated using emission factors applied to activity data, these products that we use called Edgar and Gaia and IPCC bottom-up estimates are actually in very good agreement at the global scale to top-down emissions. The top-down emission estimates come from our nitrous oxide measurements and using those to constrain what we think the emissions are going from the land surface into the atmosphere. Those are constrained at about 17 teragrams of nitrous oxide nitrogen per year, with a total anthropogenic source of about 7.3 teragrams, which is increased by about 30% over the last 3 or 4 decades. And their best estimate of agricultural emissions, again, is about 4.1 teragrams of nitrous oxide nitrogen per year. Another concern that we have is the fact that nitrous oxide emissions seem to be very climate sensitive. So in this paper, Tien and others used an ensemble of land surface schemes that simulate nitrous oxide emissions and showed that temperature alone could significantly increase the amount of emissions that we see globally by about half a teragram per 1 degree C temperature increase. So this is a pretty strong feedback. We actually commented on something similar back in 2017 in a paper we published in the Proceedings of the National Academy of Sciences. And I'll talk about that a little bit later, but we found that some of the largest emissions occurred in very warm and wet spring periods. So getting a handle on the sensitivity of how these emissions are going to change in a sort of warmer and potentially wetter world is a really important line of investigation and one that has, I think, a lot of uncertainty. My objectives for today is to basically ask these 3 questions. What is the benchmark for regional reactive nitrogen emissions, and are these emissions well constrained? Ask the question, what drives hot moments and interannual variability? And then what are the potential implications of these budget uncertainties and climate change on our potential mitigation pathways? Okay, so in the US Corn Belt, we're applying roughly now somewhere between 7 and 8 teragrams of synthetic nitrogen to the system each year. This trend suggests that we're adding 1 new teragram of synthetic nitrogen to the system every decade. And one of the things we were concerned about is our timing of fertilizer in the spring is being impacted by the fact that we're getting wetter conditions in the spring and then more extreme rainfall events that are happening in the spring. So this can have important consequences for increased runoff and indirect emissions. I'll be talking about direct emissions and indirect emissions. Direct emissions are those emissions that are occurring directly from the farm field. So after we've applied nitrogen fertilizer we keep track of the direct emissions from that system. And then the indirect emissions are those emissions where you have had runoff of nitrogen through tile drains and eventually getting out to rivers and streams, riparian zones, and we calculate those as indirect nitrous oxide emissions. We also have a significant amount of nitrogen being added to the system through the large livestock population that we have here in the upper Midwest and in the US Corn Belt. Based on IPCC estimates using emission factors and activity data, it is suggested that about 2 teragrams of nitrogen is added to the system each year, or recycled within the system each year as manure nitrogen. So that obviously has important implications for both nitrous oxide emissions, but as I'll show later, some of these large animal feedlots down here along the Minnesota border with Iowa, it's also responsible for very large ammonia emissions. I'm going to show a little bit of some aircraft data where we have flown around some of these facilities to estimate their contribution to atmospheric ammonia. I think it's pretty well established that these top-down approaches, where we take atmospheric measurements and we compare that to bottom-up approaches, i.e. based on chamber-based approaches or using emission or activity data multiplied by emission factors, that we really have an important problem here in the Corn Belt in the upper Midwest. Previous work by Court that was based on aircraft measurements, and Miller using tower measurements, and then our own data using tall tower measurements have all suggested that nitrous oxide emissions are somewhere between 3 and 8 times or 9 times greater than what the bottom-up emission estimates are. That's been sort of an ongoing sort of debate, and the sort of top-down community is pretty similar in their estimates, and the bottom-up community are pretty similar in their estimates. In the most recent study, an interesting paper that was just published this past year in Geophysical Research Letters by Ken Davis's group down at Penn State University, they flew a bunch of aircraft transects through the Corn Belt and observed very high anomalous nitrous oxide concentration. So if you see, so these are the tracks that they flew. Over here is just one example of the nitrous oxide data, very fast observations from the aircraft. If you look down here, this would be the background concentration of our atmosphere, somewhere around 331, 332 parts per billion. These enhancements that you see occur when you fly over agricultural fields and strong sources, and you get this very large anomaly or enhancement of nitrous oxide. They estimate that the flux density was about 1 nanomole per meter squared per second for this time period, which would be about 10 times greater than our best emission inventory estimates based on the latest EDGAR, and about 2.5 times greater than some of the modeling work that was done using descent simulations. So after a sort of significant number of years, we're still pointing to this sort of large discrepancy between what the top-down observations suggest and what the bottom-up observations indicate. So one hypothesis that we have been exploring is that perhaps this discrepancy is related to the fact that we have a lot of drainage, a lot of river systems in the upper Midwest, and that we have done a poor job of estimating the magnitude of the indirect nitrous oxide emissions from this landscape. So my student, Peter Turner, and Natalie Schultz, that you see here, floating down the Mississippi River in a canoe, making chamber measurements, trying to estimate nitrous oxide fluxes from these systems, published a nice paper in PNAS several years ago that suggested that indirect emissions were considerably higher than what bottom-up estimates were suggesting. So they looked at 9 stream orders, 19 different stream systems, and accumulated over 200 observations using this sort of measurement setup. And then in the smallest sort of headwater streams, we used direct chamber measurements. We didn't have to use the canoe apparatus. But in their measurements, they suggested an exponential decline in emissions, where the highest emissions were observed for headwater streams. So right at tile drain flows, ditches near agricultural systems. And then as expected, you see that flux would decline as a function of stream order. So when we got to the Mississippi, for example, stream order 9, the emissions were relatively insignificant. That work suggested that the indirect emission factor was somewhere between 0.7 to 3%. Okay, so the total amount of nitrogen added to these systems, roughly 0.7 to 3% of that would come off as nitrous oxide. In the original IPCC 2006 report, they had a default value that ranged from about 2.5% to 0.75%. So it was actually in better alignment back in 2006 to what we actually were observing. And we were sort of making the point in this paper that emission factor should be increased to reflect these large emissions from these networks, stream networks. Well, of course, that's a relatively small data set when you consider how much spatial variability and heterogeneity there is across the landscape. So this is just an example of the stream order data set provided by Horizon Systems for just a little section of the US Corn Belt. And the point I'm trying to make here is, it's going to be very difficult, to scale up these emissions and to characterize these different stream networks. And so that has led us to using this top-down tag tracer approach, where we're using tall tower observations to try to estimate not only the total budget, but also to constrain what is a direct emission from agricultural fields versus these indirect emissions from stream networks, wetlands, etc. So in this approach, we use a weather model to provide input to what's called the stochastic time integrated Lagrangian transport model. So this is the model I was describing in one of the early slides of this talk that describes where do particles come from, tracing them back in time from the tall tower. So this is used to estimate the concentration source footprint. So we use the weather model to provide input to STILT, which then traces these particles backward in time. Each hour, we release about 500 particles and trace that back in time for an entire month. As I'll show here today, we've been doing this now for 11 years, and that works out to about 30 million particles that we've traced backward in time in order to estimate these concentration footprints. In the second step, we have to take an initial guess at what the emissions are. So we use the traditional EDGAR products. This shows EDGAR version 4.2, but now we're using EDGAR version 5. We've also used things like the community land model and Peter Turner's indirect emission estimates using a GIS data product to estimate the indirect emissions. So that sets up these prior emission estimates, or our first guess at what we think the emissions are. Then in another step, we identify which of these sources have the strongest influence on the tall tower observations. And so basically what we find is that if you look at the emission sources that come from the EDGAR database, some of them, like industrial processes, really don't make much difference in terms of our emission estimates as observed at the tall tower. So we eliminate those sources and go with only those sources that actually have a significant influence on the tall tower estimates. Then in a final step, we actually use a Bayesian inversion where we optimize these emissions that were significant and important to the process. And we use a scale factor approach where we either turn up the scaling factor or turn down the scaling factor. It's like a gain function, and basically force agreement between the tall tower observations and the modeled observations that we have obtained through this process. So in a sort of a simple cartoon of what we're doing, we take the monthly concentration footprint that we estimated, and we multiply that by the a priori emissions. And in a perfect world, that would give us the nitrous oxide concentration that we observed at the tower. But that doesn't happen because there are big discrepancies between what the tower observation is and what these a priori emissions multiplied by the source footprint, what they simulate. So we use a cost function where we're forcing agreement between the tall tower observations and the modeled observations. And we take that footprint information, this is called the Jacobian matrix, and then we adjust that by these scaling factors. And this, the nice thing about this Bayesian approach is that it includes errors and uncertainties in both the modeling processes and in the scale factors or the initial guesses of the a priori emissions. So this cost function is minimized to force agreement between the tall tower observations and the modeled estimate, while considering the uncertainties in those a priori emissions in the scaling factors and in the modeled observations at the tower. Okay, so we can get into what the observations now show us. So after tracing backward in time, roughly 30 million particles over this 11-year period, we estimate a mean emission of about 400 gigagrams of nitrous oxide nitrogen for the region. So this works out to a flux density of about 0.35 nanomoles per meter squared per second. And so based on using 11 years and coming up with this average, this works out to being about 3.5 times larger than what the bottom-up Edgar emissions would suggest. If we sort of break this down then into the partitioning, we see that the direct emissions in red sort of dominate, but that the indirect emissions are also quite significant. So in May, when you have quite a bit of stream flow and runoff, the indirect emissions are quite high as well. The peak fluxes are occurring in May to June, which is about what you would expect based on the timing of fertilizer application. But also notice that in March and April, the direct emissions can be quite large, 0.35 to 0.32 nanomoles per meter squared per second. And this corresponds with the timing of snowmelt and freeze thaw cycles. Now, this is something that Claudia Wagner-Riddle at the University of Guelph has spent quite a bit of her career talking about and quantifying, where she estimates that about 70% of the annual budget could come from this freeze thaw period of time. We see it as being significant and probably accounting for at least 30% of the annual N2O emissions. One other comment I wanted to make is notice how large the propagated uncertainty is for the direct and indirect emissions. It's very hard and it's difficult to make this partitioning happen because there is aggregation error out on the landscape. You can't cleanly distinguish direct from indirect emissions. And so the starting uncertainties that we start with in the Bayesian approach are a few 100% for the indirect emissions and about 100% for the direct emissions. And after the inversion is completed, we see a reduction in uncertainty, but it is still relatively large. I should back up here. I just want to make two comments here. The largest emissions that we've observed in 2012, about 585 gigagrams of nitrous oxide nitrogen. This occurred in the warmest spring in the observed record. So in the last 122 years, 2012 was the warmest spring on record. And this coincided with some of our largest emissions that we've seen. Interestingly, 2019 was one of the wettest and coolest years on record. And this is one of our relatively low emission years. But that was followed by 2020, which was then a relatively warm spring. And so we think that the combination between wet antecedent conditions, which we observed in 2012, and of course 2020, because 2019 being a very wet year, coupled with warmer springs, gave rise to higher nitrous oxide emissions. That's something we're still working through with this interpretation. So there is some sensitivity of nitrous oxide flux to air temperature, but these relationships are not statistically significant. Now, part of the problem is relatively large uncertainty and relatively few years in the time series in order to do this kind of analysis. However, if we just look at the N2O concentration observations, which is I'm showing down here in the right-hand panel, and we look at those as plot those as a function of air temperature, we see a pretty interesting relationship. So I want to point out, because we've been making these measurements since 2010, and these are hourly values that have been binned into 0.15 degree temperature bins. We have 75,000 observations going into this plot. And what we see is that right around 0 degrees C, this is that freeze thaw period, we see an uptick in the nitrous oxide concentrations that we observed. But then there's also this quiescent period after that has happened. And then as nitrogen has been applied in the spring, you can see here from the color bar, I'm showing you the day of year. So you can see that during the spring and early summer, as temperature increases, the amount of nitrous oxide that you see in the atmosphere increases. And then when you get beyond about 30 degrees C, you see this rapid decline in the amount of nitrous oxide that is in the atmosphere. Background values, if we think about sort of measurement sites like up at Niwot Ridge in Colorado that are distant from agricultural sources, they would have a background nitrous oxide concentration now somewhere around, getting close to 330 parts per billion. So these, what you see here, are enhancements above that value. So we think this is indicative of the temperature dependencies of things like denitrification. And then perhaps getting later in the season, later in the growing season, as nitrate has been used up for plant growth. And then when we get higher temperatures, we don't really produce more nitrous oxide, and we start to see a decline back to more sort of our background values. If we look at an ensemble of these nitrous oxide measurements, that's what I'm showing here. This is the ensemble of all years stacked together. You can clearly see that there's this important freeze-thaw period of time where the nitrous oxide concentrations go up. You can see that it's quite episodic. And then this quiescent period that you see here, and then again, an increase in nitrous oxide concentrations likely following fertilizer application in the spring. The image that you see down here is really sort of a heat map that I just wanted to use to illustrate what's happening. But this is based on wavelet analyses, basically looking at the significant periods that have power in this particular signal. And you can see that the heat map really shows you that there's this important spring thaw period where we have increased nitrous oxide concentrations. Then this sort of period with very little activity. Then I think we have fertilizer being applied, and then temperatures warming up, where we again start to see those nice enhancements of nitrous oxide in the atmosphere. This period accounts for about 30% of the N2O emissions to the atmosphere. And this period you see here, the main spring growing period, accounts for about 55% of the nitrous oxide emissions. So about 85% of that N2O emission to the atmosphere really is contained in these two periods. So if you're thinking about mitigation strategies, these are sort of a couple periods to really think about in terms of processes and things that we could do to help limit and prevent those emissions from occurring. Of course, precipitation is also important. And we started to look at how precipitation events, individual events, and then enhanced precipitation like wetter springs would affect nitrous oxide emissions. And so I operate a mesocosm facility here at the university, and each one of these chambers that you see holds about 9,000 pounds of soil. And we can probe using these ports looking into the soil profile. And then we have these chambers that are measuring nitrous oxide emissions from these treatments. We found relatively little influence of enhanced precipitation on nitrous oxide emissions through some of these experiments. What did emerge, and this is really something that is well documented in the literature, is this water-filled pore space of around 55% or so. This is where, Bowman back in the 90s or early 2000s published a paper in Nature commenting on this importance of water-filled pore space on nitrous oxide emissions. And we also see, the same thing. So we should think about this more as sort of the optimal condition. And so this has got me thinking about going back to those annual nitrous oxide emission estimates using the inversion approach and trying to better understand what water-filled pore space might have been like during those years. Of course, those data are hard to get, and still sorting through some of the Cosmos data in order to try to estimate what that water-filled pore space might have been. Okay, I wanted to switch gears and talk a little bit about our ammonia work. As we know that it also is a concern where we see increasing trends over time. This is a very nice paper by Warner that was published in 2017 in Geophysical Research Letters. And it's basically showing you all the ammonia, some of the key spots where we see increasing trends. So for example, here in the upper Midwest, increasing trends in other major agricultural regions over this particular time period. Back in 2017, we were able to establish a couple different analyzers at the base of the tower to start measuring ammonia. Many of you know, and I think Richard will comment on this, and ammonia is a really difficult gas to work with and to measure. What we're doing here is pulling down really high flow rates from the tall tower, dropping the atmospheric pressure, and then we heat the tubing. You can see that the tube is all wrapped here. And we're really trying hard to prevent any sort of condensation from taking place, which would really kill your ammonia measurements. So we've been comparing a Los Gatos system with Picaro's system and making these measurements at multiple heights on the tower. We also send up known concentrations of ammonia and examine how we recover that and what the response time of these systems are in terms of quality controlling some of those measurements. If you look at our time series, you see some similar patterns to nitrous oxide, but one thing I want to point out that is pretty interesting, in 2017 and in 2020, we observed very high ammonia concentrations in mid to late November. So here in Minnesota, a significant amount of manure is applied in the late fall. And in these two Novembers, 27 and 2020, these were unusually warm Novembers. This couple-week period where we saw really, really high temperatures, people were complaining about the air quality in the region. And you could really see that we could detect what the problem was. Part of that problem was these high ammonia emissions that were taking place. So we're starting to use these data now to try to understand and use similar modeling approaches to estimate what the regional ammonia emission is. Now, this is work that was just recently published by my postdoc student, Cheng Hu, Geophysical Research Letters. And he was using the weather research and forecasting chemistry model. And what you see here are the three domains that we use to run these simulations. So the model, in this case, we're actually solving for each grid box. In the innermost domain, D3, we're solving at a 5-kilometer resolution. to estimate what the nitrous oxide emissions and deposition are. As a starting guess, just like in the previous N20 work I described, here we're using the National Emission Inventory 2011 database to estimate these spatial emissions. But what Cheng did was he adjusted those according to the EPA trends so that we had the most realistic estimate for these initial guesses of the emissions. I should also point out that computationally, running all the chemistry in WRF Chem is very expensive. So it would take about 1 full week of computation time at the supercomputer here to complete about 3 weeks of analysis. That's pretty heavy sledding in terms of making changes to your code and doing the simulations over time. In his initial comparison of the WRF Chem estimates versus what we see or observe at the tall tower, he showed that nitrous oxide concentrations were much higher at the tall tower in both May and June and July in most years compared to these simulations that you see here, for example, 2017, 2019, 2018, the sort of stippled bar graphs. He also compared this more spatially to the Amine site, so the passive network that gives you ammonia observations every 2 weeks or so. And we saw similar differences there as well. After applying scaling factors then to those initial emissions, in order to force good agreement between the tall tower observations and the WRF Chem modeling, Cheng showed that you would have to increase the emissions by about a factor of 1.75 in May, in June, and then in July about 1.64. So this is not nearly as bad as what we saw for nitrous oxide. And then in August and September, he showed that you would have to sort of dial down the gain because WRF Chem was actually overestimating the amount of nitrous or ammonia that we would see at the tall tower site. So overall, the mean growing season scaling factor had to be increased by a factor of 1.3 in order to force better agreement between what we think the NEI adjusted emissions are and what we would estimate based on the tall tower observations. Taking that analysis a little bit further and using the WRF stilt approach, we estimated then going back in time for 2020, 2019, 2018, and 2017, we estimated a regional emission estimate ranging from about 879 gigagrams of ammonia nitrogen upwards to over 1,000 gigagrams of ammonia nitrogen per year. This is a little bit lower than what Cheng would have estimated using his model, but because it was computationally so expensive, that is sort of one of the reasons for using this simplified WRF stilt approach. So if we put together then the regional ammonia and nitrous oxide budget, we have a nitrous oxide budget on average that was about 400 gigagrams of nitrogen. And the ammonia budget, based on Cheng's work, would suggest about 1,400 gigagrams of nitrogen, giving us a total of 1,800 gigagrams of nitrogen just being lost to the atmosphere. So this counts for about 23% of the new synthetic nitrogen being added to the system each year. So that's a significant cost or loss in terms of nitrogen use. So just one sort of final thing I wanted to mention. This is ongoing work where this spring we just flew our first aircraft campaign with the goal of trying to constrain ammonia emissions from both farm fields and then these large feedlot facilities. So we teamed up with Scientific Aviation out of Colorado, and you can see here we've got a couple of different Picaro analyzers. We made some modifications to the aircraft sampling system so that we shortened the Teflon sampling tube as short as possible to reduce some of those adsorption, desorption effects related to ammonia. And then we went on a 10-day campaign quantifying these different source regions. And this is work that Alex Free is currently working on. You can see here the different transects we flew. Basically, we flew a set of curtains so that we could, at the end of the campaign, use these curtains and knowledge about wind direction and planetary boundary layer height to estimate the fluxes from that approach. You can see here in this panel some of the high frequency ammonia concentration measurements. These are the observed, and then Alex has been running the WRF Chem model to see what it would have estimated those ammonia concentrations would be at that particular time and that particular altitude. And you can see that for some places, we are significantly higher, especially for some of these large facilities, livestock facilities. So that is still very preliminary work, but that's something that we're hoping to finish up here in the new year so that we can say something about sort of how well we are constraining agricultural fields versus some of these large feedlot facilities. Okay, so I wanted to just revisit our 3 questions. So what is the benchmark for regional reactive nitrogen emissions, and are these emissions well constrained? Well, I would say that I've presented sort of what we think are the long-term benchmark for nitrous oxide. On average, it's about 400 gigagrams of nitrous oxide nitrogen per year. Is it well constrained? Well, that's an important question. I think we still have this large discrepancy between bottom-up process studies and sort of our top-down approach. So until we can better reconcile those differences, I think we have large uncertainty in these emission estimates. We especially have large uncertainty in what the indirect emissions. I think that's a real challenge. And I think that the reason that we get sort of better agreement between bottom-up and top-down approaches for ammonia has something to do with the fact that ammonia has less indirect emissions as compared to nitrous oxide. I think that's a more complicated cycle to solve. Question 2, what drives hot moments and interannual variability? Clearly, the freeze-thaw phenomenon in the early spring is an important factor in determining how much nitrous oxide emission we have. So that is accounting for about 30% of the annual emission. And then, of course, the growing season is an important nitrous oxide emission period. And what determines that interannual variability for that period, I think, is really determined by antecedent moisture conditions. Are we getting close to optimal water-filled pore space? And then how warm it is. I'm making the argument that warmer temperatures seem to be causing these larger emission years, but I think we probably still need more data to really sort out some of that relationship. What are the potential implications for budget uncertainty and climate change on mitigation pathways? Well, certainly with this kind of large budget uncertainty between, for example, not having a good constraint on the indirect emissions, I think has real important implications for how we tackle mitigation. We definitely need that benchmark to see if mitigation is actually working. We also need to know, where we can put the most effective effort into helping to reduce those nitrous oxide emissions. So hopefully this work provides some important things to think about in terms of the timing. For example, the freeze-thaw period of time versus the growing season, and then thinking about how to mitigate the direct emissions versus the indirect emissions. And of course, climate change is, I think, going to play an important role here with increasing precipitation and more extreme precipitation events. I think that's going to really have a big impact on the partitioning of direct versus indirect emissions. And of course, if temperature enhances nitrous oxide emissions and ammonia emissions, then we have to probably adjust our mitigation strategies so that we can have greater reductions. This will be important moving forward, as we've sort of signed another agreement at Glasgow to reduce our greenhouse footprint. The nitrous oxide part of the story, there's some real sort of tangible things there that we can do to help contribute to that greenhouse gas reduction. So with that, thank you so much for your attention. And if I can answer any questions, I'll do my best.
Thanks, Tim, for a really interesting talk. Are there any questions? I'll start off, Tim.
Okay, Rich.
So your microbiome study, you've got a number of ports. Where are you finding most denitrification and nitrification occurring in depth-wise in those columns?
So we haven't actually done that work yet for nitrous oxide, and that is something we have planned and we're proposing to do. I can say that what we've mainly focused on there is the chamber measurements with precipitation scenarios, but I also want to comment on that we've been using designer microbes as another mitigation strategy. So we've teamed up with a company called Pivot Bio that I assume some of you have heard of. And they have been providing designer microbes that are intended to reduce the amount of synthetic nitrogen that you need. And so we have been evaluating in different treatments of nitrogen applied with their designer population of microbes, and then evaluated how much nitrous oxide emissions were reduced. And I can tell you that so far it's not significant enough, I would say.
Go ahead, Cliff.
Hi, Tim. Thanks for a great talk. I really, it was really interesting to see your work. I just had a question about the ammonia work, and because ammonia is such a, let's say, a sticky gas and has such high partitioning with water vapor. I'm curious about what your analysis shows relative to, let's say, water activity or association with water in the atmosphere, and how that affects your measurements.
So do you mean, so if I look at the effect of relative humidity on the ammonia concentration itself?
Yeah, for example, and I was also thinking perhaps about, after rainfall events and soil moisture, whether or not that's a sink or, so just curious about that.
Yeah, so actually, it's really interesting that you mentioned after rain events, because one of the things that we have puzzled over is some of our flight campaigns. We're flying one transect on one day. We saw large emissions, and then after a rain event, flying after that rain event, the same transect, we have seen deposition, or what seems to be deposition. So with respect to the tall tower, I can't really answer your question. One of the things we do is we look for large changes in relative humidity to filter the data, so that we don't have these large step changes.
Right. Okay. No, anyway, really super fascinating work. So
thanks. Thank you, Cliff.
Yeah, thank you.
Appreciate that.
Okay, so Tim, so I have another one for you.
Okay.
And we've got a number of people on this call that deal with drainage tiles, and you're talking a lot about indirect sources of N2O through the drainage, and your estimates of the estimates that you've derived, do they include actual drainage flow estimates based on precipitation and soil water holding capacity? And Or is it just sort of a flat, you've got this stream pattern and therefore it's emitting at X amount?
Yeah, so it's the latter. So what we did is quantified the emissions across those streams, and then had to estimate, in order to get the emission factor, what we think the amount of input is in terms of nitrogen. So that was all done using stream flow estimates and nitrogen application estimates at a watershed scale. But the actual emission estimates are just chamber-based approaches. Now, something that we're doing to follow up on that is we've been measuring nitrate in rivers and streams at much higher frequency and actually mapping some of those nitrate concentrations. This is work that John Baker has been doing, and really showing some interesting features of the seasonal dynamics and how land use is impacting those nitrate concentrations. So for example, this past year, where we had very little precipitation, we had very little stream flow and very low nitrate levels. And then it's late in the fall, as precipitation picked up, we've been seeing sustained and super high nitrate concentrations. And so you can take that data and then estimate, using piston velocity, what the nitrous oxide concentrations are likely to be from those rivers and streams as well. So the other thing I should mention is we just got funding from NSF to now start to look at the nitrous oxide composition, or the isotope composition of nitrous oxide. And so one of our hypotheses is that the indirect emissions, because it is derived from rivers and streams, is going to have a different isotope composition than nitrous oxide emissions from farm fields. And so we're hoping that we can use some of that isotopic information to then interpret what the isotope composition is on the tall tower observation. So we're going to have an N20 isotope laser at the tall tower looking at the isotopes and isotopologues and isotopomers of N20. And hopefully with that information out on the landscape about N20 sources and its sort of unique isotope fingerprint, we're hoping that that will help us better constrain these direct versus indirect emissions.
Any other questions? Okay, I guess we're all satiated.
Well, thank you so much for your attention and all your questions. Really appreciate the opportunity.
Yeah, thanks for coming. Oh, Cliff, you had a question?
No, just clapping.
Oh, that's a clap.
Thank you, Cliff.
Okay, thanks so much, Tim.
Thank you. Bye-bye, everyone. Have a good afternoon.
Bye.